discharge will start increasing. You will find that the head will be decreasing, and for each situation one can measure the power supplied to the motor, and maybe multiplied by some efficiency, you can find out what is the actual power given to the pump. Then one can calculate the overall efficiency, that also can be plotted. So this is general variation. Now you have the maximum efficiency point I have indicated. So corresponding to that, you will have a head, you will also have a power and all those things. That is supposed to be the design point. All other points, even discharge above or below, they are all off design points. Some pumps will have always duty along the design point. Some may have off design duty also. So in this, essentially the speed of the pump is kept constant. So it's a constant speed operating characteristics. Now the head versus discharge for 3 different speeds. So if you find out the head versus discharge for different RPM, okay, so you should have a method of varying the speed of the pump, or rather the speed of the motor. So if you keep the speed at 500 RPM, you get the curve, the bottommost curve. So you have limited shutoff head, then the discharge is also limited. When you increase, or when you double the speed, you will find that the head has increased, the shutoff head has increased, correspondingly the discharges also will increase, the power required also will increase. Then you have another curve that is corresponding to 1500 RPM. So there the shutoff head is more, the final discharge is also more. Okay, so this type of characteristics is called the head discharge characteristics of the pump characteristics. Now here I am showing the system characteristics. Okay, you have a pump system, the pump is there, the motor is there, okay, the suction is connected to the sump, some pressure gauge is there at the exit, then a valve is there. Okay, here there is no static head that is in the discharge, it is at the level of the water in the surface, in the sump. Now I have given 3 curves here, so each one corresponds to the particular say valve position. So you keep the valve position same. Now to send more discharge, what you have to do is increase the speed of the pump. Correspondingly, the head also will be more. So more head, more discharge. Okay, that is the first valve position. Now corresponding to another valve position 2, you get another curve. Little consideration will tell you that for position 2, you would have closed the valve a little more. Okay, then for third position, the valve is little more closed. So you have 3 system characteristics. Okay, earlier we had seen 3 pump characteristics for different speeds. So now you have 3 system characteristics. Okay, this is another set of system characteristics. You find that the system characteristic starts with some static head, Hs. You can see that the water level is there in the sump. The final flow level is always at a height Hs. So the pump has to minimum work to produce the head Hs. Okay, so that is some sort of a minimum starting speed in which you produce a head Hs. Now again, for 3 different valve positions, you will be able to get 3 system characteristics. Okay, so these are system characteristics with static head. The difference you can see in the previous one, the system characteristics start with 0 head, but in this the system characteristic starts with a finite initial head Hs. Any doubt so far? Okay, I'll move on to the next one. this is important. The pump system interaction. Okay, you have a pumping system, a pump, a motor, the water in the sump, then the exit valve is there. Okay, you get the head discharge characteristics, head versus discharge. So the pump will be run at a constant speed. Okay, and you see the red line, that is the pump characteristics, and the valve also will be kept at a particular position, and you have the valve characteristics or the system characteristics. Okay, you find that there is one intersecting point. We say that okay, so you have the system characteristics, you have the pump characteristics, and both will intersect at a point. So when this pump works now, it will produce a head equal to H and a discharge equal to Q given by the intersection point. Now you see a pump system interaction for three different system characteristics. You have a single constant speed pump characteristic, the red one, and you have three system characteristics. Okay, system characteristics 1, system characteristics 2 and 3. So you can think of three intersection points. So at one valve position, you will get the operating point OP1. So correspondingly, you have Q1 and H1. If you close a little more, you will move over to the operating position 2, where you have a slightly reduced discharge Q2 and a higher head H2. If you close the valve a little more, you move over to the operating point 3. Correspondingly, you will have a higher head H3 and a lower discharge Q3. Okay, so this is the pump system interaction for three different system characteristics. Now you see pump system interaction for three different pump speeds, but a single system characteristics. The single system characteristics is indicated by the green line, and you have three pump characteristics denoted by the three red lines. So the top one is the pump characteristics 1 for 1500 RPM of the pump. The next one is the pump characteristics for 1000 RPM. The next one is the pump characteristics for 500 RPM. Now you have the intersection points. The first operating point 1, which will give you a head of H1 and a discharge Q1. The second one, you will get a reduced discharge and a reduced head. The third one, you will get further reduced discharge and a reduced head. Okay. Now pump system interaction for two pump speeds and two system characteristics. Okay, the two pump speeds, one is 1500 RPM, the other one is 1000 RPM. The two system characteristics are SE1 and SE2. Okay, so the valve is indicated. You find that there is a static lift. That is why the system characteristics start from a particular height. Okay, now again you see many intersection points, the operating points, the operating point 1, 1 corresponding to system characteristics 1 and pump characteristics 1. Then here you have the operating characteristics 2, 2 corresponding to pump characteristics 2 and system characteristics 2. So correspondingly, you will be able to identify what is the head available and what is the discharge available in these situations. Any doubts so far? Okay, are you able to hear?
Yes, sir.
Yes, sir.
You are able.
Yes, sir.
So no doubts so far. Okay, I will move on to the next one. Okay. Now the net positive suction head. See, the pump users, manufacturers, they talk about net positive suction head. Okay, it is connected with the suction side. Okay, the NPSH is defined as the total absolute head above the saturated vapor pressure head corresponding to the liquid temperature. Okay, so NPSH is the total absolute head. That means at the suction point S, you find out the absolute pressure divided by rho g. So this pressure head is there, plus the velocity head, because it is the total head, static head plus dynamic head. So half v square by g. Okay, this is the total absolute pressure head above the well, it has to be above the saturated vapor. So you have to subtract the saturated